This is Bob McFetrich with Beckwith Electric, and I'd like to thank you for downloading session 5 of our series on integrated volt var control. In this session we will be talking about the SCADA Heartbeat. First, as a recap of what we're trying to achieve overall, is an integrated volt var system in which we're going to deploy a combination of fixed and switched capacitor banks that are going to help us improve the power factor and reduce system losses. And we're also going to coordinate these as additional voltage support so that we can reduce the operations on our LTCs and our regulators, and at the same time we can flatten the voltage profile across the circuit so that we can reduce the voltage when needed and thus reduce the load. So that's the overall goal of an IVVC system. And as we discussed in the last session, session 4 on architectures, there are two basic approaches to accomplish this. One would be using a system where no communications is in place and we're coordinating the operation of the regulators, LTCs, and capacitor banks via settings in each control. And the second approach would be a more centralized approach with communications, where we have a separate software application that is collecting data across the entire system and making decisions as where the best place to raise or lower the voltage is. And so in this session we're dealing mainly with communications. So with a centralized approach, we typically see a SCADA Master or a distribution management system, DMS, that will be pulling all the devices from switch capacitor controls to feeder regulator controls to line regulator controls to LTC controls. It will also in all probability be pulling data from protective relays and downline reclosers. And from this data it will do some sort of analysis and then send out commands to individual controls to have them operate. A second way of doing this with communications is to have a more decentralized approach, where we take, instead of having one central piece of software looking at the entire distribution system, we have software running in each substation, typically on a substation automation platform or remote terminal unit, RTU. And that substation automation system, or RTU, will pull only the capacitor banks and regulators and LTCs that are normally fed from that system or that substation. So those are the two different approaches we're going to be looking at, and how the heartbeat is required for both of them. So in general, this would be our typical architecture for a centralized or decentralized IVVC system. We have our controls out in the field outside the substation. We also have controls inside the substation. We have some device, either a SCADA Master, DMS, or substation automation platform, that is going to be collecting data from these devices and then ultimately making decisions. So the first thing we have to define is what types of data that we need to have to make those decisions. And typically we're looking at things like tap position, voltages, currents, watts, and VARs. And then status, is the bank open or closed? Is the LTC or regulator control and local manual? Do we have a blown fuse on a capacitor bank so it's out of service? So we're trying to determine whether each of the devices is operational or not, and then we're attempting to get metering from each of the devices so that we can then take that metering and pass it on to some other piece of software to make the actual decisions. And depending on the complexity of the system, there may be only one component or two components. For the more complex DMS and SCADA Masters, they may run a real-time load flow analysis and then have the output of that load flow analysis go into the volt var application. Typically substation approaches will not have the load flow, and a lot of the SCADA systems may not have the load flow. They may just go into a tabular or a lookup type table to determine the operation. But it's ultimately the goal of the IVVC application software to determine the optimal voltage and VAR flow, and therefore sending the correct commands to any given control. So the IVVC software will then, after making the determination if any action needs to be done on the voltage or the VAR flow, what corrective action needs to be done and who is going to be responsible for doing it. So if the voltage is a little high, are we better to have a capacitor bank turn off, or are we better to have an LTC or a regulator lower the voltage? If we're lacking VARs, obviously we need to switch a capacitor bank on, but which capacitor bank will be the most effective bank to get the VARs where they need to be? Once that decision is made, the IVVC application will then send commands, and then it'll be up to the SCADA Master to then send those commands out to the individual controls. So that's the overall philosophy, whether it's a substation approach or a central approach. We're going to collect real-time data. We're going to do some analysis on that data. We're then going to direct SCADA to send commands out to individual devices to correct any problems that may be on the system. Now, for the local controls, there are two ways that we can do this. The first way is what's called remote manual. In the remote manual mode, all controls will be in remote manual, meaning that they will not be making any decisions on their own typically. So if you're a capacitor bank, you're not looking at the voltage or the VAR flow to determine whether to open or close. You're awaiting a command from SCADA to tell you whether to open or close. Likewise, if you're a regulator or an LTC control, you're not looking at the voltage to determine if you need to raise a tap or lower a tap. You're waiting for SCADA to instruct you to raise a tap or lower a tap. The advantage of doing it this way is that it doesn't require as much processing on the SCADA Master, and the commands that are being sent out are digital output, which binary output commands, which don't take up that much bandwidth. The disadvantage of this type of system is if we lose communications, then our controls are in remote manual and they're not taking any action. So if the SCADA system were to go down or the communication system were to go down, we would have either small pockets or possibly our entire system not have any voltage regulation until SCADA came back up. The other disadvantage is typically to make these decisions, the algorithm needs to have the data updated much quicker than the second method we're going to talk about. So when you're looking at an IVVC centralized approach, you need to know whether you're going to run in this mode, and if so, how often the data needs to be updated into the algorithm, and how often the algorithm needs to run to reevaluate your system. The second approach is remote bias. In this approach, we're going to leave all the controls in local automatic mode. And what we're going to do is we're going to dynamically change settings in individual controls to cause them to operate on their own. So instead of telling a capacitor bank to close, we're going to change either its VAR setting or its voltage setting so that it then comes to the conclusion on its own that it needs to close. The advantage of this is that your controls are always in local automatic. So even if we were to lose SCADA communications, our controls are still going to be functioning. They may not have the most optimal settings as the load conditions change on the system, but at least they still are in automatic mode and we do have some sort of operation. The disadvantage to this type of system is it is more complex on the IVVC software. It's much easier to say close than it is to calculate the settings, to know what the settings are in that control, and then to calculate and know what you need to change them to in order to get that control to decide on its own to close. It also requires a little bit more bandwidth when it's sending a command, and that analog outputs typically require more bandwidth than digital outputs. There are some SCADA masters that also don't support analog outputs. So if you have a system that does not support analog outputs, you will not be able to use the remote bias mode. You will have to run in the remote manual mode. So, in either mode, we do have to protect ourselves against a loss of communications. As a central program, we are anticipating that the central system is going to make the majority of the decisions, and if the decisions can't get out to us, then we have to know to fall back into a mode where we start making decisions on our own. And that's where the SCADA Heartbeat comes in. So the basic definition of a SCADA Heartbeat is some sort of signal that instructs the local controls that they still are receiving valid communications from the Centralized Master. If we lose that heartbeat, then that is our signal to go into local automatic. Now, the type of heartbeat, there are basically two types of heartbeats we're going to talk about, and which heartbeat we select is going to be determined both off of our architecture and off of which of the modes. So we've described the two different modes. Now we need to go back into the architecture a little bit more and see why that would impact the type of heartbeat used. So, with the remote manual mode, as we said, heartbeat is critical because SCADA goes down, we stay in remote manual, we have no regulation. In the remote management or the remote bias mode, it's not that critical because we still do have settings. So as a rule of thumb, typically we're going to have to send the heartbeat more frequently if we're going to run in a remote manual mode versus a remote bias mode. Typically a heartbeat in remote manual is typically set every 3 to 5 minutes, where in the remote bias mode we may go a half hour to an hour between heartbeats. Now to the architectures. In this first architecture, we are going with a centralized approach, and the IVVC software or application is embedded in the SCADA Master itself to the extent that there's no way the SCADA Master can be polling with the IVVC system not running. If that's the case, then we can go with what we would refer to as the standard heartbeat. And in the standard heartbeat, the control is going to use any valid messages it receives from the SCADA Master to its address as the means to reinitialize the heartbeat. So for instance, if this control were to have a heartbeat of 5 minutes, when it receives a valid message from the SCADA system, it starts counting down from 5 minutes. If it gets to 0 before it receives another valid message from the SCADA system directed to it, it will go out of remote manual and enter local automatic mode and stay in that mode until the SCADA comes back again. So this is a good way of doing it if we have direct communications from the master to each individual control, and the IVVC system cannot be shut down without the SCADA Master also being shut down. And the reason this is advantageous is it requires no additional communications. We don't have to send a heartbeat signal to each individual control. Our normal polling is doing that automatically for us. So, with that in mind, we still want to have some capabilities in that local control for two reasons. Number one, for backup. If we lose the heartbeat, we need to be able to regulate the voltage by closing in cap banks or raising, lowering tap positions. So if SCADA is down, we still need to have some sort of local operation to fall back to. The other reason we want to have some smarts in our local controls is to actually supervise the IVVC software. So we want to set limits in each individual control. For instance, I don't want the voltage to ever get above 126. And if the SCADA Master sends a command to me, and me acting on that command is going to make the voltage go above that level, I need to disregard that command first of all, and then secondly, I need to inform the SCADA Master that I did not act on that command because it would have driven me above the high voltage limit. So we want to be able to block SCADA commands if they're going to drive us outside of predetermined limits. Likewise, even if we don't receive a command, if our upper voltage is 126 and we're seeing the voltage rise, maybe because of a reduction in load, and that voltage gets above 126, we may need to have the ability to open up automatically even if SCADA didn't request it. So with most of the controls, even in the remote manual mode, they may still operate, or they may block an operation from SCADA if that operation is going to drive them outside of a voltage limit. So our next approach is going to be a centralized master that is going through a substation. So in this case we have a SCADA master, but it is not pulling the devices directly. The devices are being pulled from the substation RTU, and then their data is being passed up to the SCADA. In this case, we would not want to use the standard heartbeat, because if we were to lose the communication link between the SCADA and the RTU would still be pulling the controls would still be seeing valid communications, and therefore they would remain in remote manual even though the centralized system can no longer send commands down to them. So in this case we would have two options. Option one is we could program some logic into this device that says if we lose communications here, we need to stop communicating here so that each of these can come out and go into local automatic mode. The other method would be to select the second option for a heartbeat, which is the direct heartbeat. And the way the direct heartbeat is going to work is SCADA has to actually write a value into the timing register of each control. So again, if we want a 5-minute heartbeat, SCADA would write a value of 5 minutes into the timer. The control would start counting down, and if it reaches 0 before SCADA writes a new value into that timer, it will go out into local automatic even if it still does see valid communications. So this is an area where we would want to use the standard heartbeat. Now, a disadvantage of the standard heartbeat is it does now require a dedicated message from the SCADA system to each individual control, and therefore that is going to eat into the bandwidth requirements on our system. We still want to have the intelligence in the local controls. We still want to be able to block the SCADA commands just like before. So another approach would be a distributed approach, where the SCADA master is not running the IVVC system, but a substation automation system is running it. The advantage of that is twofold. Number one, it reduces the communication requirements. So instead of the SCADA master having to pull each individual control, now it's just pulling the substations, and the substations are pulling the individual controls. That allows the communication path to be much shorter. So instead of having to go 20, 30 miles to get back to the SCADA master, I may only have to go 2 miles back to the substation RTU, and now I can start looking at mesh technologies and unlicensed technologies for the communications. It also helps in that instead of having one large system to implement, we can now implement in smaller chunks or in phases. We can take one substation at a time, apply the amount of capacitor banks we need, have all that communicated back to the substation, and then we're going to allow the substation to do the IVVC algorithms. One of the disadvantages of this is the substation is typically only going to see the devices that it's normally attached to. So it's going to pull all the regulators and capacitor banks off the feeders leaving that substation. But if we were to have a fault and do some sectionalizing, we may have devices now that are on our feeders that weren't normally, or we may have devices that were on our feeders that now are not. And so that adds a bit of complexity that is much easier to handle at the central master approach. So you may have a combined approach where you're running in a distributed or a substation-based approach, But if you have sectionalizing, it may fall back to a central approach. Now, another thing to consider with the heartbeat, back to the central approach, is in this case we have our SCADA Master, but the IVVC software is not integrated directly into the SCADA, but it's a separate application that can be opened or closed. So, if we were to use the standard heartbeat in this case, the SCADA could be polling, but if the IVVC software was shut down, there's nothing to send commands to these controls to open, close, raise, lower, and we would want to come out into local automatic mode. But because we still have valid communications, we would not. So in this mode, we would again select the direct heartbeat, and we would have the IVVC application actually be the one to generate the command to send the new heartbeat timer to each individual control. So it would generate a command to the SCADA system would pass it down to the control. If the control did not receive a new heartbeat timer, it would know that the IVVC application was not running, even though we are communicating, and it would therefore go into local automatic mode. And again, we have the distributor to the combined approach. In this approach, again, the SCADA Master may be pulling some of the controls directly, but we may have an intermediate RTU pulling other controls. So again, if we were to use the standard heartbeat, it may work in these, but if this link goes down, the RTU would still be pulling, and therefore these controls would not know to come out, and they would stay in remote manual. So the two ways to fix this problem are, again, to have logic in the RTU to where if we lose this link, it stops polling, so these come out, or we would go with the direct heartbeat, and therefore, if we lost this link, it would not be getting the timer from the IVVC application, and it would come out on its own, even though it was still communicating to the substation. So, we have two different heartbeats we can deploy. The standard heartbeat is the easiest to implement. It's one setting on the control, which is the time value, and the time starts counting down, and as long as we receive valid communication from the SCADA, we automatically reinitialize that timer. The direct mode is a little bit more complex, and that we still have a timer value setting in the control, but what reinitializes that value is not any valid communications, but a specific write from the IVVC software into that register to bring it back to a new positive value. If we reach 0 before we get that, then we're going to come out on our own. The disadvantage, obviously, is it's going to require additional bandwidth to do that. So one of the ways we can get around that additional bandwidth requirement is to go with a global addressing scheme. So DNP has global addressing built into it, but some vendors also built in multiple global addresses. So in the case of these controls, we can program 3 different addresses into the same control. I can program the unique control address, but then I can also assign it a separate feeder address, and as a third address, the substation address. With this approach, if the IVVC software sends a heartbeat command to this address, only this one control will update its timer. If it sends the same command to this address and all 3 controls have that same address for their feeder address, then all 3 controls would simultaneously update their timers. And if we were to send it to this address, then every control with that address would update its timer. So this gives us 2 advantages. If we have every single control in the system have the same station address, then with one single command we're updating all the heartbeats simultaneously, which is going to reduce the bandwidth requirements greatly, but it's also going to synchronize so that they all come in and out of heartbeat at the same time across the entire system. Now, there are a couple other heartbeats besides the normal one for IVVC, and that is because we have dedicated applications that need separate heartbeats. The first of which is voltage reduction. So if you do remote voltage reduction to your regulator and LTC controls, and you place them into a reduction mode and then they lose communications, you don't want them to permanently stay in that reduction mode. So what we can do is have a separate heartbeat for reduction, say 15 minutes. And once SCADA places the control into reduction, it'll stay in reduction for that amount of time and then automatically come out whether SCADA is still pulling it or not. And if SCADA wants it to stay in for longer than 15 minutes, SCADA would have to send a new value to that heartbeat before it reached 0 to continue it on. Likewise, there's a second application called remote voltage bias that's found in LTC and regulator controls. The purpose of this is to use an end-of-line reading from SCADA to tell us what the voltage is at the end of the line. Typically, regulator and LTC controls will use a function called line drop compensation so that they can account for the amount of voltage drop due to load conditions. We know as the load goes up, the voltage drop increases. So if I want to keep the voltage constant near the end of the circuit, I have to vary the voltage where I am to accommodate that amount of voltage drop. And that is based on the amount of load going through that system. But with the advent of distributed generation, we can have DG between the regulator or LTC and the end of the line. If that's the case and that DG is putting power out onto the circuit, then the regulator is not going to see that. So for instance, if I've got 600 amps that I'm regulating and I have no DG online, all 600 amps have to come through the feeder regulators. And I would compensate appropriately for that. But if I still have 600 amps of load on the circuit, but 200 amps of that is being supplied by the downline DG, the regulator is only going to see 400 amps and therefore will undercompensate, not thinking there's as much drop as there really is, and you can get into under voltage conditions at the end of the circuit. Therefore, if we can just get a measurement and have SCADA tell us what that end of voltage is, we would know exactly where we need it to be to get that end of voltage up. So for instance, if the end of voltage is 118 and I want it to be 120, I know I have to raise my voltage by 2 volts to get that down up to 120. But again, if SCADA loses communication with either the regulator control or the downline sensor, the control will be getting a stale value, and we don't want that. So we would have a separate heartbeat for that gets initialized every time SCADA writes the new end-of-line voltage value into a register. And if we go so long without seeing that, we'll come out of heartbeat and go back to using our general line drop compensation settings. So in summary, the heartbeat for IVVC is used to allow field devices to know whether the centralized system is up and running, and therefore to inform the local control as to whether it needs to stay in a remote manual position or return to a local automatic position. And the type of heartbeat used, standard versus direct, is going to be determined by the architecture. And the time between when we've got to send heartbeats out is going to be determined by the type of heartbeat. If it's a standard heartbeat, then we don't have to do any time. But if it's a direct heartbeat, we do have to do a time. And if it's a direct heartbeat, then we've got to know which of the architectures. I mean, whether we're running in remote manual or remote bias. If we're running in remote manual, we need to send it more frequently than if we're running in remote bias. We also have additional heartbeats that may be there for specific functions such as voltage reduction and remote voltage bias. So I hope that provides a little better understanding of why we need a heartbeat and why we need to implement different heartbeats for different architectures and therefore have different intervals that they're sent, and how that can impact the communication system that you're going to need to have. So we thank you for your time, and we hope that you'll be downloading our next session. Thank you very much.